In this video, we will discuss about single electron devices. What are single electron devices? Single electron devices are based on the controllable single electron transfer between small conducting island. Actually, single electron devices, the concept of single electron devices started in 1909. In 1909, Millikan first illustrated the manipulation of single electrons. However, the single electron device cannot be implemented in solid state physics because until late 1980s there is limited fabrication techniques. So due to limited fabrication techniques until 1980 there is no so improvement in single electron devices. What is the basic physics of single electron device? Assume a small metal sphere, also called island, with zero net charge. This is a metal sphere with zero net charge. In this state, no electrical field occurs beyond the border of the island. You see, this is the border of the island, and beyond this border of this island, there is no net electrical field. When an external force F brings a single electron, suppose minus E, from outside close to the island, an electrical field E is generated by the non-zero net charge. You see, this is a metal sphere having non-zero net charge. Suppose by applying a force F, you bring a electron here, and this is the direction of the motion of the electron. And if this is a electron and this is a metal charge, a metal sphere having net charge, zero net charge, then you will get a electric field along this direction. This will be the direction of this electric field. So electric field will be generated by this non-zero net charge or by this island. The electric field is oppositely proportional to the square of the island size. You see, you have a relation that this field will be proportional to inversely proportional to island size. That means if the island size will increase, then electric field will decrease, and vice versa. If you decrease the island size, then electric field will be increased. So if you decrease this island size to nano size or to nano scale, then you will get a very large electric field. So this is the basic physics of single electron device. The electrical field is oppositely proportional to the square of the island size, so it may become very strong for nanoscale structures. Examples of single electron devices. Single electron devices are basically single electron box, single electron transistor, single electron trap. So we will discuss one by one. First, let us discuss about single electron box. This is the basic diagram of single electron box. It consists of a small island. This is the small island separated from a large source. This is a large source. This small island is separated from this large source by a tunnel barrier. You see, this is a barrier which is called tunnel barrier. And this is called the gate. Gate is another electrode which is used to apply an electric field. Through this gate you can apply electric field on the small island. You see in this picture, you apply electric field through this gate. So when you apply electric field through this gate, what will happen? Electrochemical potential of this island is changed. You see, there will be change in electrochemical potential of the island by applying electric field in this gate, because this and this electrochemical potential will affect the tunneling effect. This will affect the tunneling effect through this barrier. If we plot a graph taking gate voltage along x-axis and the island charge, the charge which is produced in this island along y-axis, then you will get a graph like as given below. You see, this is the simple diagram of the single electron box, and this is the graph when you take gate voltage along x-axis and average number of island electron along y-axis, then the nature of the graph will be like this. And here I have shown you the difference between a single electron box circuit and by simply connecting a resistor. When a capacitor is charged through a resistor, the charge on the capacitor is proportional to the applied voltage. This is the simple physics what we know. If you charge this capacitor through this resistor, then what will happen? The charge on the capacitor will be proportional to the applied voltage, and there is no sign of quantization. But when the resistor is replaced by a tunnel junction, you see here this resistor is replaced by a tunnel junction. So when a resistor is replaced by a tunnel junction, a conducting island is formed between the junction and the capacitor plate. You say conducting island. So conducting island will be formed between the junction and the capacitor plate. And in this case, what will happen? The average charge on this island increases in steps. There will be increase in the charge in a step-like manner as the voltage is increased. You see, as the voltage is increased, the charge will increase like a step manner. So which shows quantization. And the steps are sharper for more resistive barriers and lower temperature. This was from the experiment of single electron box. Now we'll discuss about single electron transistor. A single electron transistor is a sensitive electronic device based on the Coulomb blockade effect. What is Coulomb blockade? A Coulomb blockade is the decrease in electrical conductance at small bias voltage of a small electronic device. You see, this is a small electronic device. Here you have a conductive island sandwiched between two tunnel junctions. These are two tunnel junctions, and you have a conductive island in between two tunnel junctions. And in this device, the electrons flow through a tunnel junction between source and drain to a quantum dot. Between source and drain, electrons are flowing to a quantum dot. You see, you have a third electrode. Here the gate is the third electrode, and the electrical potential of the island can be tuned by a third electrode known as gate, which is capacitively coupled to the island. This is a capacitor. So through a capacitor, this gate is coupled to this island. And you will see, if you apply the bias voltage Vg, this is the bias voltage Vg. If the bias voltage Vg is less than the Coulomb blockade, then no electron can tunnel through these two junctions, because there is no sufficient energy to charge the island. And if the bias voltage Vg is greater than the Coulomb blockade Vc, then the current will flow through the circuit as given below. So if you plot a graph taking the bias voltage Vg along x-axis and current along y-axis, then this will be the nature of the graph. And from the graph it is clear that if the bias voltage Vg is greater than the Coulomb blockade voltage Vc, then current will flow through the circuit like this, and also in the reverse direction. And if the gate voltage Vg is increased, and the bias voltage is less than the Coulomb blockade, then the current will oscillate, which is called Coulomb oscillation. You see, this is the nature of the graph, or which is called the Coulomb oscillation. Now let us discuss about single electron trap. Electron trap are essentially localized regions where there is a deficit of negative charge or an excess of positive charge. If in a region you have excess of positive charge or a deficit of negative charge, you say this region is a electron trap region, or you may say single electron trap. So single electron trap is essentially a localized region. Single electron trap has more than two tunnel junctions in the island, which is separated by tunnel barrier. You see, this is a simple single electron trap device, and you have more than two tunnel junctions, and this is the array of island, and these are the tunnel junctions. So you have more than two tunnel junctions, and which is separated by tunnel barriers. You have you can see you have tunnel barriers, and as discussed previously, this is the gate, and initially the gate is provided with a sufficiently high voltage, as a result of which the electrons are driven into the edge of this island. When the gate voltage is decreased to the initial value, what will happen? First, you increase the gate voltage, then you decrease the gate voltage. So if you decrease the gate voltage to the initial value, what will happen? The electrons are trapped in the island. If you decrease the gate voltage, the electron will be trapped in this island, and the electrons can be removed from this trap. When it is trapped, it is called electron trap, and that is why it is called electron trap device. And the electrons can be removed from the trap by reducing the voltage. This is the basic principle or physics behind single electron trap. The lifetime of trap depends upon also thermal activation. Single electron trap operates like an internal memory. It can store two or more bits of information by changing the gate voltage. So in examination we will get question like what is a single electron box, what is single electron devices, and discuss various single electron devices like single electron box, single electron transistor, single electron trap, etc.